Okay, so I'm going to be creating a second order differential equation that shows how the output of the circuit is related to the input for time is equal to greater than 0. So if we look at the switch over here, we can see that at time is equal to 0, this switch will actually close, therefore completing the circuit. So if we want now for time is greater than 0, you can make this switch closed. So now that the switch is closed, we will now analyze the circuit and create two equations relating to the current and voltage. So we'll be doing KVL and KCL. So to get started, I will start with KVL. Okay. So we know that the input of the circuit is Vs. And now we're going to be finding the KVL. So the resistor, the first resistor multiplied by the current, which is IT, is going to be equal to the voltage drop across that resistor. So we have R1 I of T plus the voltage drop across that inductor. So we can represent that voltage drop as L, the derivative of the current, over dt. And now we also need the voltage over here. And this is simply just equal to V of t. So this is our first equation. And that would be the whole current, or voltage, sorry, flowing through this circuit. All of the voltage in the circuit will be equal to V of S, so the voltage source. And now we need to make an equation that represents our current. So now we can write down I of t is equal to the current over here and the current over here. Since we know that our current going from here to this node right here is going to be equal to I of t, we can make that I of t. And the voltage going down from here, right here, can be represented as V of t over resistor 2 plus the the current flowing here. And we can represent that in the same way as we did for the inductor to represent the voltage. We can do the same thing for the current going through this capacitor. And that can be represented as C dV over dt of time. So now that we have both of our equations, what we actually want to do is make everything in terms of Vs. So over here we have to get rid of this I of t, and we also have to change this into a voltage. So to do that, what we can actually do is we can already sub this part of this equation in for I of t. However, we cannot do that same thing for this over here. So to do that, what we can actually do is find the derivative of this side, or of this equation. So the derivative of I of t is actually just going to be equal to that. And that is going to be equal to the derivative of this, which is 1 over R2 dV over dt plus the second derivative, the second order derivative, or yes, just second derivative of dV over dt, which is going to be this right here. So now that we have that, what we can actually do is just take this equation and now sub in this part of this equation. So that's going to be Vs equals to this part. I'm just going to on brackets because we just subbed it in R1 plus L, and now we're going to be subbing in our second order, or just our other KCL equation over here. I'm going to make that a little bit smaller. And what we can also do is just add our plus V of t. So now that we have this equation, now we're just going to simply just solve for it. When solving for this, we just literally just multiply this in, sorry, not solve, but simplify. So now, when we multiply this in, we'll get R1 over R2 V of t plus R1 multiplied to C dv over dt plus L over R2 dv over dt LC and our second order. Plus V of t. So now that we've got to this part, what we actually want to do is represent this equation in a form where we have dt as our second order as our first, and then so on down the line with all of our derivatives. So we have Vs is equal to LC d squared of t over, this is supposed to be dv of t over dt. And then we're also going to have our R1 C. I'm actually just going to show you, I'm just going to quickly do this real quick. L over R2. So these two have a common factor, which is going to be our derivatives of the dv over dt. So we can just take that out. dv over dt plus our final bit, which is just these two. So when we do this, we will end up with R1 over R2 V of t. I will actually just do two steps real quick just to show this as a better example. And what's going to happen with this over here is pretty much we're just going to take the R1 over R2 plus 1, because now we're going to be actually taking the common factor of V of t out. So this can just be rewritten as this. So now that we've gone to the step, we're very close to the final solution. What we're actually going to do is to represent this as the output of the circuit. We're going to divide out our LC. So we're going to have Vs over LC. And since we're dividing this out, this will actually get divided out throughout the whole equation. So what will happen here is we're going to have d squared V d of t plus, now over here we're also going to do CL, CL, over here CL and CL. So what we're going to end up with over here is going to be R1 over L, since these two cancel out, plus, now here we're actually going to end up with L, or 1 over R2C dv dt t plus, now we're going to do the same thing over here, and what we're going to end up with is r1 plus r2 over r2 cl vt. You can put this v up here, whatever, it doesn't really, actually, no. And we're going to have vt over here. And with that being said, we have now made an equation that will represent the output of the circuit related to the input.